So good morning, everyone. My name is Lukáš Ferkel, and on behalf of the Hybrid Geotabs Project Consortium, I would like to uh, warmly welcome you here in Prague on this workshop and also on the project meeting. We have still some technical details with the stream, but it will shortly come up. I apologize for that. We had some cleaning lady tackle around with the cables during the night, and our preparations got vain. Good question. Maybe it was not a lady. So for today, what's our program? In the first block, we will have an introduction to our project and to MPC control, followed by a discussion or debate led by Wim Boydens. And then we will have a presentation on MPC on demonstration buildings, which will be presented by Philip Jorissen, and Jiří Ziegler is not here, so Jan Schulz will give the presentation, followed by, again, a debate. And then we will have a lunch. And after the lunch, we will have a trip to the Liebesnice school, where MPC is controlling the school with hybrid geotab system, and by bus. And then around 6 o'clock in the evening, we will return back here again by bus. So now I would like to ask Professor Jelle Laverche to give some brief intro to the project.
Okay, so good morning, everyone. Also on my behalf, welcome here in Prague. So the reason that I stand here in front is that I am officially the project leader for this project, and so it is my duty to welcome you all and to say thank you for participating in this project and coming to this workshop where we present part of the results and have a discussion about the objectives of the project that we are conducting, and that we will have a project meeting on, as Lukáš introduced, for the next 2 days. And to start the day and to give you an overview of what the project is about, I would like to bring to the front Eline, who is our project manager, and who has prepared a presentation about the different parts of our project. We are still waiting for the technical stuff to get resolved, so in the meantime, just meet the person sitting next to you if you don't know him yet or her yet. This will facilitate the discussion in the rest of the program. And we're getting there, yes. All right, perfect. We have a picture. So without further ado, I would like to present to you Eline Himpe, the project manager who is part of our team at Ghent University.
Good that you saw it. Good morning. Thank you for the introduction, and again, welcome to all of you. In this presentation, I will give like a 10-minute short overview of the technology the Hybrid Geotubs project is focusing on and what we are trying to reach within this project. Of course, then later today, we will go deeper into the aspect of model predictive control. So, the Hybrid Geotubs project is a European-funded Horizon 2020 project that started about 2 years ago. So we are about halfway the project right now and have about 2 more years to go. What is it all about? What is it all about? The project actually starts from the concept of geotubs buildings. For those who wouldn't know yet, geotubs is a combination of tubs, which is thermally activated building systems, also known as, for example, concrete core activation, where heating, cooling systems are integrated within building elements such as floors or ceilings, allowing for radiant heating and cooling of the building. The connection of these for providing the energy to these systems with geothermal energy is then called geotubs. So the main components are the tub system and a geothermal bore field combined with a heat pump. And of course, some control to manage all of that. Okay, good. To go a bit more in detail, at the moment that there is a heating demand in the building, cold heat will be taken from the underground, which is at a more or less stable temperature, and using a heat pump, it will be upgraded to a higher temperature in order to heat the building at temperatures which are very close to comfort level. So temperatures of between like 25, 35 degrees. In other moments, like in summertime, when cooling is needed in the building, actually the cold or the temperatures underground, being, for example, around 17 degrees, can be integrated into the building in a passive way, or if needed, it can also be introduced in active cooling to even lower the temperatures. But usually with passive cooling, we can already do quite a lot. Also, the technology allows to have seasonal storage of the heat or cold into the ground, in which the ground serves as a heat source and or heat sink. So in the winter, the cold is stored in the ground, which is then used in the summer. During summertime, the heat from the building is again stored in the ground to be used in wintertime. The geotubs technology already exists for quite some time and has quite some benefits. In terms of thermal comfort, for example, tubs is a radiant heating and cooling system, which is very nice for having high thermal comfort. Also, because also we use the thermal mass of the building, we can store quite some heat to reduce, for example, peak loads. On the side of the geothermal energy, there is a possibility of integrating low-grade renewable energy sources, leading to higher amount of renewable energy in the building. And because of the small temperature difference between the underground and the building, that's also very good to have an efficient operation of the heat pump. However, there are, of course, a number of challenges, otherwise we would not be here today. Challenges with regard to the geotubs concept. On the side of the tubs, the high thermal inertia of a tubs floor makes that it can be difficult to reach also comfort in moments that, for example, a very sudden increase in heating or cooling demand is reached because, for example, the sun hits in the building or many people come into a room, so which might suddenly increase heating or cooling demand, and which cannot always directly covered by the tubs. Second aspect can also be with regard to acoustics or dehumidification. On the geothermal energy part, there is, of course, the heat balance of the ground. As I said, in cases or in buildings where there is a lot more heating or a lot more cooling demand, it's not always possible to balance the heat in the ground. So that's something that should be further looked at, and can also limit the amount of cases in which geotubs can be applied. Also, the availability of geothermal energy is case dependent, and heat pumps are still quite a high investment. Therefore, we have a first solution in the project that is not to combine the geotubs with secondary systems, both on the emission side and the production side. So that is why we say the project is called hybrid geotubs. The hybrid solution in terms of emission systems can be to combine the tubs with other emission systems such as radiators, fan coil units, and so on. On the geothermal or the production side, we can combine geothermal energy with classical non-renewable or with renewable resources to assist in the heat production where needed. For example, to reach a better balance in the ground every year, or to reduce investment costs, so that we can use the geotubs at its point where it is most interesting and most efficient to use, and cover the remaining demand with, for example, less expensive energy sources. Then, of course, this brings this integration with secondary systems into a hybrid concept, brings along even a number of extra challenges. One of them is related to the control of the building, which will be the topic of the remainder of today. Traditional control of buildings is usually based on rule-based control. However, when we come into a building that is quite complicated with integration of various systems, it becomes more and more difficult to design and also time-consuming to design and develop these controls, to use them, to have them decently working. On the other hand, we have there the solution of using model predictive control, but also there quite some developments need to be made. But that is, of course, the further topic of today. Also, on the level of the design of such a building, there are still quite a number of challenges. For example, today it is often based on personal experiences of some experts who are designing these projects, these buildings. So an optimal balance between the geotub system and the secondary system, that is still a question we are working towards. Of course, also the control of the building might have an effect on the sizing of the components, so we should also take that into account. A second solution, therefore, in the project is the further development of model predictive controls to use in hybrid geotubs buildings. And a third solution is then about the integrated design of the concept, in which we take into account the geotubs and secondary systems and also the effect of the control. The goal or the aim there is to have a more optimal sizing of the concept and to provide easy-to-use guidelines or design methods that can be applied by engineers, architects, and a wider public in the future, so that we can avoid to have a lot of time-consuming studies with dynamic simulations and so on. So all these challenges brought a number of people together in this project, which we call Hybrid Geotubs, but the long name of the project is Model Predictive Control and Innovative System Integration of Geotubs in Hybrid Low-Grade Thermal Energy Systems. So Hybrid MPC Geotubs. It's a Horizon 2020 project, so funded by the European Union. And here you see also the team of people who are involved. These were most of the people that were at our previous consortium meeting, but you will see many of these people are in the room or will present their work later today. In the consortium, it's quite important to mention, we have a mix of academic partners, small and medium-sized enterprise partners, and also some industrial partners. To shortly introduce the academic partners are Ghent University, the KU Leuven. We have there also Maastricht University, the Danish Technological University in Copenhagen, and Imergo Cluster as being partially university, partially SME partner. Then we have a number of two design institutes Lemon Consult from Switzerland. We have Geother, experienced in geothermal energy use from Spain, and two larger industrial partners being Viessmann and Upponer, who are also here today. And then finally, of course, in our communications, you will have contact with Liz with Climate Futures from UK and REVA, the European HVAC Association, which you might already know. I'm going to go a bit to the last part of the presentation. In the project, we have quite a number of demonstration and case study buildings. These buildings we use to implement the developed controls, for example, in the project, but we also use them to validate the concept. These buildings have a geotabs technology at this moment, which is often already hybrid. During the project, we are implementing their new controls. We are playing around with the design of the buildings and evaluate their actual performance. So in these buildings, we measure energy uses, we evaluate the performance so that we can actually demonstrate the actual energy performance, thermal comfort, and so on in the project. One of the buildings is located close by. That's the school you see down there, which we are going to visit also this afternoon, and you'll hear more about that. Finally, a final step in the project is also to improve the commercial attractiveness of the hybrid geotabs concept, where we are looking towards a broader implementation of the hybrid geotabs. We are working towards a business plan, but also towards a more easy sizing of the different components within the system, and also provide, for example, solutions for what in situations of renovation where no tops is available, we are looking towards ceiling panels that also have some thermal inertia. In conclusion, the project is the main components of the project are to have a hybrid solution that is with model predictive control and an integrated design and operation of the system, aiming at an improved energy efficiency, good thermal comfort, and of course also cost a nice cost balance. And we are looking towards this in feasibility, pre-design, design, commissioning, and use stage of the building. With this short introduction, I will give the floor to the next speaker, and via the social media, via our website, you can of course find much more information about the project.
Thank you very much, Eline. And now is the time for Damien Picard of KU Leuven, who will give us a brief introduction on how MPC works and what is it about. Damien has been working quite a few years on MPC control now, and so he's the best person here to give us the introduction to MPC now. So, Damien, the floor is yours.
Thank you. I will start with putting my own presentation on. What does that mean? It's maybe already open, yeah. I should work on my Slavic skills, but... Good morning, everyone. So I have the pleasure today to introduce you the concept of model predictive control. After my presentation, Philippe Joris and normally Jerry, but you, Jan, will give a presentation on the practical aspect, how do we implement it in real buildings. I will try to keep my presentation sufficiently short, such that you can ask whatever questions you want to, but keep in mind that if you have really questions about the practical aspect of it, it's maybe better to wait next presentation so that you have the total view. And before I start, I would like to know who has been working on designing buildings and HVAC system in the room? And who has been working on designing control for HVAC system and buildings? Okay. All right, let's get started. So firstly, as I'm the first presenter, I always have to give a bit the overview. And I just want to show you a couple of disasters when the Earth is not reacting as we want to. So for example, if it's not raining, we have a big troubles to get food. When there is a tornado or a flood, it's extremely destructive. So when Earth is not kind to us, we are in big trouble. But the problem is that we are not very kind to the Earth either. It's a fact that there is a global warming which is happening fast, and we are speaking about just a huge challenge to keep the temperature rise under 1.5 degrees by 2050. So the politics is working on this type of numbers, so it's pretty short time, and there's a lot of actions which needs to be done and which is partially being done. So with this, I just want to, as you all know, it's time to change our behavior, to change our use, to use and to need less, and it's time to focus on energy efficiency. But what's quite interesting is that the building sectors, as you may know, is actually using a tremendous amount of energy. According to the report of International Energy Agency and International Partnership for Energy Efficiency Cooperation, the building sectors use worldwide 120 exajoule, which is about 30% of the total energy consumptions of all sectors of economy. So this is a really substantial numbers, and it's also responsible for 30% of the global CO2 emission. And the report also make kind of some speculation that if we apply now the most efficient system to all existing buildings, we could save roughly 50% of the energy used by the building sectors. So at the top of that, it also gives some graphs about the energy used per square meters of buildings in the different countries. It's difficult to read here, but what I want you to show is that we are working on making buildings more efficient, and you see that the specific power of installed power in buildings is going down, as well as the energy used per square meter for buildings. So that's a good news, even though it's not a really sharp decrease of energy. But what's more alarming is that actually if we compare this with the increase of surface of building surface being built every year, we see that there is an increase between 20 to 60% in most of the countries in Europe of building floor area. So this totally overcompensates the reduction of specific installed power for the different buildings and specific energy. So, or the energy use of buildings is still sharply increasing. So that puts us into a big challenge, as we are one of the main factor of energy use, and as it's not decreasing, but it's increasing still every year. So how can we try to use less energy? The first step is not control, even though my presentation today will be about control. But the first step is about getting a better design of your building. Only once your building is well designed, you can be pretty efficient. So passive design is a topic which is more and more present. Here are a couple of examples of buildings. This is the solar wind building that has been designed by Boydens Engineering, and which is one of the case studies of the project. So with this, I just want to stress that the first step is always passive design. The second step is try to get some efficient HVAC system in your building. And this project focuses on geotabs, of hybrid geotabs building. This is a very efficient system using, as Eileen has said, some heat pumps and also some concrete core activation, which is a type of floor heating. But yeah, it's important so to try to get efficient system in your building to also have as little CO2 emission as possible. But then the last step, which is very important, is control. Control is sometimes a bit overseen, while it plays a crucial role, and it has an increasingly important role. The first reason why it's important is that our buildings start to be bigger and bigger, especially if you think about Asia. Buildings are just there, enormous, but also in Europe, we have really large buildings. And as we try to get more and more efficient, we try to implement renewable energy into our buildings, we often end up with not a single system, not only a very big gas boiler supplying all the heat for all the building with just radiators to feed that heat, but we start to have combination of system. And this project is also really focusing on hybrids buildings, when we have several ways of generating heat for the building. A heat pump, for example, in combination with a gas boiler, and then every space also has different ways of getting energy into it. Might be taps or floor heating, and on top of that there will be a ventilation system which you can also heat or cool. There might be some fine coil units on top of that. So when you have a wide variety of systems which can give heat or cooling to the different zones of your building, of course you have to be careful that you do not counteract each other, that you are not destroying energy. And also you have to know which system is best to use when, such that you are energy efficient as much as possible. But also buildings need to be comfortable. This is something also included in our project. Our partner from Maastricht are analyzing what's the effect of thermal comfort on our health, but also on our productivity. And we see that there is a very clear correlation between feeling comfortable at work, not having it too warm or too cold, and your productivity. It again coincides with a lot of money for the company. So this is very important. And comfort is firstly achieved by having a good design of the building, but secondly, by having a good control. And finally, something which is always a problem is that our buildings the HVAC of buildings is oversized for the daily use. So even if you don't put any safety factor into your design, you still need to have a building which is able to provide enough heat when it's very cold outside, the coldest day outside. But most of the time it's not the coldest day, and then you end up with a system which is oversized and then which is difficult to control well. So this is so far for the introduction. Now let's go really into control of buildings. The general way of controlling a building is we have an HVAC system, and then we are going to control it with what's called a rule-based controller. And the rule-based controller is a set of typical blocks, such as the heating and cooling curves, some hysteresis, PI controller. Often, if we have a slow system like taps, you also need to define the mode of the building, if it's in heating mode or cooling mode, and that you make sure that you don't switch too fast from one to the other. You may have night setback and preheating. But if we look at a building like SolarWinds, I had a picture here. This building was intended to be a demonstrator for capabilities of renewable energies system. And they ended up with, I think, 4 different types of heat pumps into the building with pellet kettles pellet burners. They had some solar collectors, as well as even wind turbine, and they had taps into the building. They also had fine coil units, and so they ended up with a lot of system for the emission and for the production. And while my colleague Philip Jorissen was doing his PhD and trying to model all that and implement all the rule-based control, he ended up with a book of 400 pages describing how the control works. Just because it's so complex to put all these different systems into rules and to try to optimize the way they interact when it's just a very work-intensive work. And you always end up with a suboptimal solution, which needs also a lot of commissionings. What's also important is that you have to, it's very difficult to get a general framework that you can apply to all buildings. So you always have a lot of engineering to make it, and then a lot of engineering to commission it and to tune it until you achieve a good comfort and good energy. So most probably the way of the future is not anymore to try to, by hand, define all the different rules and all the different interactions into software, but much more trying to create a software where we can give the general physics of the building, or that we can give which type of HVAC is present in the building and which type of building it is, so which type of occupancy there is, which type of schedule, which type of internal gains which are being expected, and solar gains, and that we can put this more physical information into the software, and that the software is going to automatically set up which type of control signals needs to be sent to the different machines, and the software is going to take itself into account the connections between these different systems. And there's a really upcoming technology which is now everywhere, is the optimization possibilities of the computer, and the computer will then have to optimize how can we get as much comfort in the building and how can we use as little energy as possible. So this project is working on this with this model predictive control, and I would like to introduce more what's our vision about this and how we implement it. When we speak about computer starting optimizing and started thinking, I think a keyword that everybody has heard before is artificial intelligence. This is really an upcoming technology which is also taking a role in HVAC. If you think about Nest thermostat, for example, this is artificial intelligence, but there is a lot of other aspects. And I would first like to introduce it with the Google car example to show you what are the key elements of artificial intelligence. And here I mean artificial intelligence in a really broad scope, namely that the computer starts thinking and optimizing in order to control a system. So a first thing which is very important when you speak about artificial intelligence is that you need to imagine for the car, you firstly need to know what's the goal. So where do you want to go with this car? So that's the trajectory. We may also need to know some predictions, so that, for example, and some set points. So you need to know what are the speed limits on the different places on the way. It might be useful to guess where are the traffic jams, where are the traffic lights, and so what is going to decrease your speed. So that's the first element that you really need. So know where you go, know where are the limits, and have some kind of prediction so that you can anticipate things. The second thing that you need is to have a model. So if it's your computer is going to drive the car, the computer needs to know what happens if you push on the throttle. So how fast is the car going to accelerate? How fast can you brake? What happens when you move the steering wheel? You really need a model that the computer can anticipate. If I do that with this control action, that's going to happen. This is in construct with a PI controller, which does not need to have a model of what it's controlling. It's just going to apply something, see if it's going in the right direction, and if it's going in the right direction, it's continuing that direction. Otherwise, it will go in the other direction. And the last thing that we need is some feedback. So we have a model, but we know that the model is not perfect. So even though the computer thought that if I brake now, I only need 10 meters to stop, then while braking, it should always measure the speed again, measure the position again, and see if is anything happening, like is everything happening as I've predicted, and if not, the feedback is there to correct it. The feedback can also be used to improve the model if you have an adaptive model. And all these three elements, so the trajectory, the model, and the feedback, will be all included into an optimization algorithm, which will then try to get things done as efficiently as possible. And in the case of the car, that would mean to get from point A to point B as fast as possible, while ensuring a good comfort and mostly ensuring security. So let's first focus a little bit on the model, because this is a really key element. In literature and in practice, all the type of models generation is categorized in three types. The first one is a black box model. A black box model is something where you measure the actions that you put, for example, the throttle and the steer angle of the car, and you measure at the same time what's the resulting speed and what's the resulting direction. And then you are going to create a mathematical model just based on this measurement to find a connection between the throttle and the speed and the steer angle and the direction. So you do not need to apply any physics into this. It is just think about a regression curve, for example, or other type of model. It can be also neural network if you're really into artificial intelligence. It can be whatever. But what's important is that you need measurement data of your system, and then you just by applying some mathematical tricks on it, you will be able to predict more or less your system. Another way of doing it is to say, well, I have an idea how my system looks like. So I know that I have a steering wheel, and I know that I have that the throttle is connected to the engine, and that's so that there is a clear connection between speed and throttle. And then you try to put this information already in your mathematical model, and you only optimize the parameters of this model based on the measurement. So let's say that you have a general idea how the car is working, but your model is not applied to that specific car. Then you measure the throttle and steering wheel and speed and direction, and then you start optimizing the parameters of the model so that it would be really fitted for that car. That's called a gray box approach. First was the black box, this is gray box. And the last one is white box, where you don't think that you need measurement data because you have the physical equation describing how it works. For example, you know the friction law, and you can apply it for the brakes, then you know how fast it would stop. You know the Newton law, so you know how much the car, if you know the weight of the car, you know how fast it would accelerate if you put on the throttle. So this is the white box approach. The white box approach so needs a lot of parameters of the actual car in order to be able to guess how it will work. The advantage of this method is that you do not need any measurement data, and that you have more under control how this model looks like, because it's all you who define how it looks like. And then a second aspect that I want still to focus on, and then we will go to buildings, is so the algorithm, the optimization algorithm. There's some important keywords. First important keywords is objective. Objective is what you want to achieve with your optimization. And in the case of the car, I've said it's the minimum time, minimum fuel, and the maximum comfort. Then there is this optimization variable, is that actually what are you controlling? And for the car, it might be the throttle, the steering wheel, brakes, and the road that you choose to go, for example, from where we are now to the Leibniz school. Then you have some constraints. You want to stay safe. There are some speed limits. There are other users. And finally, there is prediction. So with that, you may know what's a traffic jam and a traffic light. So these are all very important keywords for optimization algorithm and artificial intelligence. And now we are going to dig into a special aspect of artificial intelligence, which is called MPC, Model Predictive Control. So I still want to give you, this picture is not there. What does it mean? Tento obrazekni.
It's not visible.
And how can you make it visible?
I don't know. There's a mistake.
Okay. No problem. So there will be one picture less in the slides, but I think we will manage. How about I just connect my computer? Yeah. Sorry for this little technical problem. It's always better when the picture's opened. So I first will want to give you a short introduction about model predictive control, how it works. I give you one last example with the cars, and then we're going to jump with buildings. So imagine you are driving your car and you are working like a rule-based controller, and in this particular aspect, for example, like a PI controller or like a hysteresis. The PI controller always look on the past, basically. Are you at the set points as expected, or are you deviating from it? And if you are deviating, trying to restore the problem. But that actually coincides with driving your car and looking at the rear mirror. Every time you see that you are going too much to one side, you are measuring the error, and then you are going to correct it. If you are hysteresis, you're just going to give a snap to your steering wheel. If you're a PI controller, you're going to do it more smoothly. But that's not how we drive a car. We, hopefully at least. How we drive a car is that we are looking ahead. Where do we want to go? So I'm going to look the 50 meters ahead. Where do I want to go? And I have a model of my car. I have been driving my car for a while. I know how fast I can accelerate. I know how fast I can brake. And what's interesting is that I'm going actually to project myself without maybe realizing ahead for the coming 50 meters. And I'm going to optimize it. I know that actually in 5 seconds I'm going to start braking. I'm not going to start now, but in 5 seconds I should start braking. And so I have an idea for the coming 10 seconds, for example, what I'm going to do. But what's interesting as well is that after 1 second or after 2 seconds, I might realize that my model was not that good of the car, and actually I was going faster than I expected. And so despite the fact that I have already computed the optimal things that I'm going to do the coming 10 seconds, I'm going to correct myself and say, no, actually, I'm going to change my action. I'm going to brake a bit earlier. And so that's extremely interesting because we have a model. We are able to project ourselves in the future. We are optimizing, but there is still a feedback mechanism. Every second, we are going to reproject ourselves in the future, and two projection after two time step is not going to be exactly the same. So we're always re-evaluating the situation and re-optimizing what we are going to do. If we look at how it would look like for the car on the way, so if it's just a hysteresis controller, it's just going to look at, oh, I'm here too far away from my set point, I should go to the other direction, and you're going to drive like this up and down. If you're a PI controller, then you need a unique trajectory. You cannot work with bounds. And you're going to try to stay on it, and every time you are getting away from it, you're going to try to correct it. What's tricky with this is that firstly, comfort is typically not a trajectory that you try to follow, but these are two bounds. There is when you are too cold and when there is too warm, but there is a dead band between these two where you could stay, and your algorithm could make use of that. For PID controller, it's not very possible. And secondly, PI controller is not easy to tune, and then you may have overshoot or like you may have oscillations, and that's very tricky as well. But MPC is just going to look ahead with what's called the horizon. So for example, that was my 50 meters, and going to project itself and see, okay, I should just stay just within these two lines and optimize. And what's interesting is when this car will be at this position, then again it's going to reevaluate until here what it should do. So I hope that with this I could make it clear how MPC works. Imagine you have a building now. If you have a rule-based controller, you may have a thermostat, a heating curve, and still, for example, so a thermostatic fan for the radiator. And again, you are going to oscillate between your set point. The thermostat is going to turn off the system or turn it on, and you are going to oscillate between this different temperature. This does not look like the best way to control your building, and especially not if you start having lots of different machines and that needs to modulate correctly and interact correctly with each other. If we look now at MPC, how it would look like, then we firstly need, so that's our building, we will need a model of that building to be able to predict how fast can the building being heated up, how fast does it cool down. We also need to have some weather forecast so that we know how much solar gains is going to come, and to, together with the building model, guess what will be the temperature rise in the building. We also need to have some occupancy forecast. Firstly, to know when are people going to be in the building. So when do I need to, when does the building need to be warm? But also because in modern buildings, internal gains causes a major source of heat, and then you may have to cool down your building. And then if you put all this information together into your optimization algorithm, then you get a curve which is multidimensional. Here I'll just show a two-dimensional curve where there is probably one point where you use the least energy and you get you still get all the comfort which is required. All right, so that was the idea. Now, how does it work in practice? The way we are doing it in this project is mostly white box, so we do not use so much measurement data to make models, but we use physical equations to make the model. And we try to have a one-to-one mapping between the reality and our model. In the project, our Czech partner is also are also using gray box approach. So we are using actually the two approaches. And I'm showing here the schematic. That's what you see on the hydraulic scheme, the different heat pump with the pump and so on. And I show you how the models look like. So there is a clear mapping between these two. And what parameters that we then have to give are valve characteristics, heat pump characteristics, pump characteristics, pressure drops in the system. And if we know all this, we can give all this information to MPC, then MPC can optimize up to each component. So can optimize the actual opening of this valve and taking into account not only the effect on the COP of the heat pump because the temperature is going to be different, but also the pressure drop of the pump. So again, here we can optimize not only the heat pump, but the heat pump in combination with the circulation pump. So that was the HVAC. Now, if we are modeling the building, we are going to divide the building into different zones, and then we can optimize the temperature of each zones. Typically, the zones is going to coincide with the HVAC zones that has been defined before. So what we are optimizing, as I've said, we can optimize valve and damper positions, pump and fan speeds, set points, and I think, yeah, I've said all this already. What's MPC really strong in is to avoid the destruction of energy. For example, if one side of your building needs heating, the other side is cooling, and hydraulically it's possible to bring energy from one side to the other side. That's something MPC is always going to do. It's also going to see if you have floor heating and ventilations, making sure that there is not one heating while the other one is cooling, except if it's truly optimal, which might be the case, but which is not often the case. And then my colleague is going to give more information about the practical implementation on how do we apply MPC into the building. Our approach is not to have to change anything from the original building management system and just to be able to override some set points with our algorithm. And with this, I would like to conclude that there is a couple of companies which are already applying it. One of the companies, Energo Cluster, who is also a partner in the project. But I think the biggest player is Johnson Control. They've applied MPC to the Stanford University campus. That's a very big campus. That's 50 megawatt gas fire plant with cogeneration. And they have been running it for a couple of years now. And they have achieved 10 to 15% of additional savings compared to the best building manager, what they could achieve in the building. So these are really substantial amount of energy savings. And also, their system can work for a very, very large campus. So that's also interesting. One of the case studies is SolarWind, as I've mentioned, and this has been also investigated to the PhD of Philip Jorisen. And in simulation environments, it could save 82% of energy compared to the RBC case. This is, of course, an overestimation because simulation environment does not include all the aspects of the building, but we are strongly hoping to have 50% energy saving in that building by applying MPC. Then there are other companies like Building IQ, which is mostly based in Australia and America. There's Johnson Control, who have a team of 40 people working exclusively on MPC. And then there are here a set of other companies also working on MPC. So it's, to me, pretty obvious that optimal control is going to come in the building. It's not obvious in which format is going to come. If it's going to use white box, gray box, black box. And it's also not very obvious if it's going to be in 5 years or in 10 years. but it's very obvious that it will save us time to apply this type of technology, and it will save us energy. So I strongly believe will come, and we are working on this project on applying it to real buildings with our approach and to contribute to that general effort. With this, I would like to thank you, and if there is any question, you may ask them, but remember that you can also write them down and discuss it during the debate after the next two presentations. Thank you.
So, thank you, Damien. Now we will have a presentation on the demonstration buildings and so now we will have a presentation on two demonstration cases that we have within our project. The first presentation will be given by Jan Schulz, who's actually my almost former PhD student. Somewhere in between submission and defense now. And he's now working with the Ferramat company, which is part of Energo Cluster, who is the partner of the project. So, Jan.
Thank you. So, hello everyone. I will have a presentation about the Liebesnice school building and MPC implementations, about the previous MPC implementation and new MPC implementation. So here's the agenda of the presentation. At first, I will shortly introduce the Liebesnice building. Then I will talk about the energy production system of the Liebesnice building. Then I will talk about the previous MPC implementation of the TAPS system. Then I will talk about about some experiment at the Liebesnice building for demand response management. And at the end, I will talk about new MPC implementation, which is only 2 days in operation currently. So this this is the Liebesnice building, a very nice building, circle building. It's a TAPS building with a ground coupled heat pump system. So it's a basic school which was opened in September 2015. There are 8 classrooms and a multifunctional hall which serves primarily as a canteen and for cultural events. So it is for 240 pupils. This building is quite simple because it has only 1 floor, and the overall floor area is 1,000 square meters. This building is called Rondel, and it represents the sun system, which means that the sun is in the middle and serves for some sports activities and free time of pupils, and the classes representing the planets, 8 planets. In the following pictures, you will see the important elements of HVAC systems, which are important for our project. For example, the TAPS system is, or pipes for TAPS are in the concrete here. This is one of the class called Venus. What is typical for classes is that They are expanding from the front to the back from the board. And here you can see the supply of fresh air, which is the pipe at the ceiling, and also the exhaust, which is on the wall. The white boards are acoustic panels, and the roof windows can be manually opened. The walls, there are also other windows which are on the at the back walls, which can be also manually opened. This is a multifunctional hall which serves for cultural events and as a canteen. There is also kitchen. Here you can see the windows at the walls. And for sport activities, there is also an athletic track. Everything you will see during the guided tour in the afternoon. So now I will talk about the energy production system of the building. As I said, it's a ground-coupled heat pump system. The heat pump can provide 55 kilowatts in heat and 65 kilowatt in cold. The bore field has 6 boreholes, which are 130 meters deep. There is a top system for heating and cooling, and also 9 decentralized air handling units for each classroom and multifunctional halls. The air handling units have also heating and cooling coils. And the heat and cold for air handling units and for tubs is provided by heat pump. The heat pump can be operated in 3 modes. The first one is heating, the second one passive cooling, and the last one is active cooling. I will explain the modes at the following scheme. It is a little bit confused, but I will emphasize the important elements. So that there is a heat pump, and there is a bore field. If the heat pump is working in heat mode, it takes heat from the ground and produce due to the compressor work provides much more heat at the secondary side. And it can provide heat either to the domestic hot water tank or to the heat storage tank. To the heat storage tank. From the heat storage tank, the heat can be further distributed to the tub circle or to the air handling unit circle. If the heat pump is operated in passive cooling mode, the cold is taken from the boreholes, and without any compressor work of the heat pump, it is distributed to the cold storage tank. From the cold storage tank, it is further distributed to the air handling unit circle or again to the tubs circle. The heat pump can be also operated in active cooling mode. It means that the cold is taken from bore field to the primary side of heat pump, and the surplus heat is from the storage tank sent to the ground again, or stored to the ground. I hope that it is clean. You will see it in the afternoon. So now I will talk about the previous MPC implementation. In the previous MPC implementation, MPC controlled only set points for supply water temperature of taps. It didn't control air handling units. So the objective was to minimize the thermal comfort violation. It means to keep the set points in classrooms and energy for taps system. The mathematical model for MPC was the gray box model and was very simple. It has only it had only two states. The one state was the average temperature in the whole building. So one temperature for all classes and multifunctional hall. And the second state was the taps temperature, meaning the concrete temperature. The MPC predicts the following disturbances: occupancy in classrooms and the hall, the ambient temperature, and all solar gains in all directions. Now let me talk about some experiment for MPC for demand as a demand response potential. It was only some experiment which took place in Líbeznice for 3 months in 2017. The objective was to control the heat pump according to the dynamic price of energy. So the objective, the goal was to minimize the the price for running heat pump in such a way that the temperature of the storage tank will be kept at desired temperature. It takes the load profile into account and also contribution of heat pump into account. We also considered the model of coefficient of performance for the heat pump. And the idea is to shift the load to times where the price is low. The system saved between 10 to 20% of end customer costs, and it also improves the grid stability because it consumes primary energy when there is a surplus of energy in electricity grid. Here I can show you some results, some real results, and the first picture is the price signal. The second picture is the taps power, and the third picture is signal for running heat pump. You can see that it runs heat pump when the price is low. Now I will talk about new MPC implementation. As I said, it's only 2 days in operation, so we don't have so much results. But it works. We will discuss it with Jiří also during the afternoon. It includes this MPC implementation includes control of both tap system and also air handling units. It considers the model of temperature in each classroom and also in hall, and also the model of CO2 concentration. It's a dynamic gray box model based on resistant capacitance model. Some parameters were tuned according to our experience from past, and also from the white box model, which was created in Modelica, thanks to my colleague Eugenii. Thank you. Here is new MPC implementation in equations. So we minimize the cost, the energy of TAPS system, and also thermal violation, temperature violation in each classroom, and also violation of CO2 concentration in each classroom, and also energy for ventilation in each classroom. Subject to our mathematical model, and there are also some slack variables to temperature set points and CO2 concentration set points. There is also constraints for maximum TAPS power and maximum ventilation power. So our model has together 28 states, 19 manipulated variables, and 9 disturbance variables. As I said, it is a discrete time dynamic model. The control period is 20 minutes. The prediction horizon is now 24 hours. It means 72 steps. MPC is implemented as a cloud service in Python and communicates with PLC at Líbeznice through some protocols of the PLC proxy. And the historical operational data are stored in database, and we can supervise them through Mervis SCADA interface, thanks to Honza Široký. The future work will be the refinement of the mathematical model and extension also to the cooling model. I would like to thanks to all project members, Lukáš and Jiří as project leaders. Thanks to Euheni and also my colleague David Charvat, which implemented the MPC in the real operation in Python. And Lukáš wanted also to talk about the Blanka Tunnel complex, if I have time. Before the lunch, okay. Because it's our largest project, and we will go through the Blanka Tunnel during when we go to the guided tour. So, okay. So thank you for your attention and questions during the discussion.
Thank you very much. And now is the floor for Philip Jorissen, sorry, from KU Leuven, who will give us a presentation on other case study that we have in the project, and that is the Infrax building, where actually the headquarters of offices, quarters of Boyden's Studie Bureau. Is it correct pronunciation? Studie Bureau Boyden's reside. So, Philip.
Thank you. Okay, so as announced already, we're here in a project where we have several demonstration cases, and we have two methodologies essentially for applying MPC. What Jan just presented was what we call the gray box approach, as Damien explained, and we're looking into 3 more cases which use a white box approach, and that's what I'm going to go in. I'm going to go into a bit more detail into the first of them, which is the Infrax building in Brussels. This is the outline. I'm going to give a brief introduction to the building itself and then explain a bit more into detail how the MPC implementation works exactly, what the workflow is for working with it, and some future plans. So, firstly, Infrax is an office building. It's illustrated here with a nice picture. It's an office building of 3,000 square meters. It's spread over 4 floors that you can clearly see here, and it's a geotabs building. So it also has 2 ground-coupled heat pumps, geothermal bore field, an air handling unit with cooling coil and heating coil. Each floor has separate VAVs with separate controls with an additional heating coil. And there are passive blinds that you can see over here. So those are not controlled. And there are active blinds also over here, for instance, that can slide horizontally in front of the glazing if required. And there's also a cooling tower on the building, which is not used all that often. So most of the time, the geothermal bore field satisfies for the cooling requirements. So here you can see again the passive blinds that are fixed. So they shade the ground floor and the first floor essentially. And then the second and the third floor, you have these movable blinds that can move in front of the window. From top view, it looks like this. So this is the building that we're talking about. What I just want to show here that from this side, we don't have too much shading. Here there is some shading from nearby trees, and mostly from this side, we have some shading. So these kind of aspects we also take into account in the building model, because they essentially, when light is blocked from nearby trees or objects, it can have a large impact on the overall energy balance of the building, since it affects how much heat enters through the windows and thus how much cooling is required. This is a schematic overview of the HVAC of the system. So everything is more or less built up around the geothermal bore field, where we have a main circulation pump that drives this circulation loop. And the first thing along this line is two geothermal heat pumps of 70 kilowatts each. And actually there's a bypass here also, which allows you to then bypass water through here, which can be used for passive cooling. So the passive cooling is either for server rooms or the air handling unit cooling coils, or it can be used directly for cooling the concrete core activation. So concrete core activation can either be used for cooling or for heating. For cooling, it's through the geothermal bore field, and for heating, it's going through the geothermal heat pumps. And then finally, we also have heating coils for the air handling unit, so that's centrally at the air handling unit. And we have smaller individual, that's this one, and we have smaller individual heating coils for the VAVs inside of the building itself. And then finally, we also have a backup cooling coil, cooling tower for additional cooling if needed. So the building is currently controlled using a rule-based controller. It's a system of Priva. They have these graphical interfaces that look like this. It's very convenient for making adjustments. And it's controlled over a backnet interface. So as Damien already explained, that's the interface that we try to hook up into. So we write directly on the backnet layer to override the existing control signals. And that means we also have a fail-safe in case of problems, so we can fall back to the existing rule-based controller implementation. So the white box modeling approach has been explained partly already by Damien. So in this, I'm going to explain here what this means for this particular case study. So I just want to repeat here that model predictive control is optimization based. It means that we're optimizing a certain specific model that controls the building, and it's a model specifically for that building. So for each building, we have to make a separate building, what we call a controller model. And of course, what we try to do is to make this as easy as possible, to lower the complexity, because we don't want everyone to have a PhD in optimization to be able to make one of these controllers. And that's essentially what the whole white box approach is about, that we try to automate as much as possible this MPC model development. And therefore we have set up this methodology, which you can read more about in this beautiful book over here. So the methodology is essentially, it consists of three parts. Firstly, we have, it's all using Modelica, and so the first part is essentially using Modelica libraries. So we have made a bunch of libraries called Ideas, and also the IBIPSA library, which is an international collaboration. And these libraries, they're essentially as a real library where you have books, but we have models on the shelves. And these models are, for instance, a heat pump model, a pipe model, a pump model, fan model, and things like that. And the idea is that you can just grab the models from those libraries, configure them with some basic properties like nominal flow rates, or for instance a valve type, efficiency curves, COP curves, and then using those models you can compose a building model. So I'm going to illustrate that a bit further in a moment, but the idea is that as a non-expert you can just grab these components, put them together, and compose a MPC controller model using those objects. And then in the third step, we take this model as an input and we automatically transform it into an optimization code. So the idea is here that we have this building model. Someone creates it using the known building geometry and HVAC design schematics that are available. Then you have this Modelica model. We pass it through this toolchain. Don't think I mentioned the acronym yet. Oh yeah, so toolchain for automated control and optimization. And out comes an executable. So the idea is that this process here is a once-through process. So this part, we do this only once, and then you have this executable. And that executable uses the initial temperature of the building and weather forecasts to compute optimal control variables. And this is essentially then something that we compute time and again, for instance, every 20 minutes in Leibniz. And in our case, currently, we're using 1 hour. And this then determines set points for optimal control, which are then tracked by lower level controllers. So this slide you've seen already, but I just want to repeat here that the idea is that with this white box approach that we make it very intuitive. So we want to be able at some point that you can just take the building schematic, read it, and map this to one-to-one. And we're not there yet completely, so that's part of the research we're still doing, but to a large extent it's already possible to make this one-to-one mapping, and essentially it's just a matter of making our algorithms sufficiently generic to be able to do this. On the building level, it's the same approach. We want to be able to do one-to-one mapping, but you've seen this slide already also. So now I'm going to explain a bit more in the case of Infrax what this looks like. So what you see here is just to give an idea, it's a graphical overview of what these libraries look like. We have here a number of packages where all these models are contained in. And essentially there are two parts which are important here. It's the building envelope, so that's this package, and then the HVAC, that's everything that's in fluid. And these are the two main parts of the building envelope. So the controls and everything, it's not in here because that's essentially what the MPC is for. We just explain how the building works using a model, and then the control has to figure itself out. And essentially the basic components of ideas, they look like this. So this is a zone model, which contains equations for zone air temperature and radiative heat exchange, for instance. And these are what we call surfaces. So this is a window model. This is an outer wall model. This can also be used as a ceiling. And this is a floor slab, essentially. And these models have parameters which are fairly intuitive. So inclination angle, so this is a ceiling, for instance, azimuth angle, so oriented towards south, surface area, and the type of roof, and things like that. So the idea is that it's not rocket science. Now, in the case of Infrax, it looks like this. Now, we didn't clean this up, and yeah, this is not that this is super clear or something, but yeah, it's just to show that we split it up here also in 4 floors. And then some separate, for instance, a hallway that's spread over multiple floors, we put it separately. But this kind of workflow is something that we want to automate further, such that this is not something you have to deal with directly. And then just to illustrate also, this is one floor which then contains more of these zones that are coupled together. And that's the sort of, objects that we're working with. So the idea is that you have zones, you map them into these zones, and you have walls which can also be mapped into a wall. So essentially the type of input parameters that we need with this approach are these things, more or less. We need surface areas of all walls, the orientation, the material layers and their thermal properties, although we have a default database for thermal properties. So essentially we just need to know what different layers are contained by a wall. Often it's the same for the entire building, so it's not too much work to piece this together. The same thing for glazing type. Is it double glazing, triple glazing? What's the U value? Things like that. And then we also need to know the location and geometry of shading devices, such as surrounding trees, or like here outside you have this row of houses at a distance of about 50 meters. So it's this kind of information, quite general, that we currently need. And just also to give you an idea, this is how we put this into a code, but it's again something we don't want to expose to the user directly. But essentially we have here a construction which is called inner floor, and it consists of a layer of gypsum, 2 layers of concrete, a layer of air, and then a particle board. So this is essentially a suspended floor, and this is the type of code that we actually have underneath. Similarly, for glazing, we have here a glazing system which consists of a glass layer of 4 millimeters, an argon air layer of 15 millimeters, and then another glass layer. And we have some transmission and absorption coefficients here. So all this information is taken into account to do the actual MPC modeling. Then to get back to the HVAC implementation, I already showed this graph. But just to repeat, we have here a bore field, 2 heat pumps, and then some things that are connected to that. So in Modelica, it looks like this. So this is the actual HVAC model that we're using. So this is a bore field. We have a pump here. This is a bypass I mentioned that wasn't on the other schematic. We have a heat pump model here, and then a bunch of connections like heat exchangers. As it was shown here, you have 2 heat exchangers, 2 pumps, okay, this is not on the next one, but so the idea is just to show you that it's even more clear for the building schematics that we're just doing this one-to-one mapping from a schematic into a model. And then here again, we have some more information about the concrete core activation. So for the 4 floors, we have 1 valve each that controls the flow rate for that floor, and 1 central pump and some valves for mixing between the heat and the cooling circuit, essentially. So based on this information and these hydraulic connections, the MPC is able to figure out what its control options are, and it's then fully automatically computes what the optimal control settings are. So now for the HVAC, what type of information do we actually need? The most important thing is, of course, what components do we have and how are they interconnected? And then other than that, it's pretty generic things like nominal flow rates and pressure drops, fan and pump curves at nominal speed, the valve types, so we have different types of valves. For the concrete core activation, we need to know the spacing between the different pipes, the thickness of the pipes themselves, the diameter, and things like that. Also sensor locations, because we use feedback from sensors to correct our model. So now also with for instance, a thermostat, you have some temperature measurement that you use to control heating and cooling. We also need those, and we need to know where they are located, more or less anyway. For a heat pump, we need a performance map. So as a function of inlet temperatures, what is the COP of this heat pump? You can also use a fixed COP, but that will of course decrease the performance of your controller. For heat exchangers, also pretty generic things like nominal heat flow rates and mass flow rates, from which we compute a UA value of the heat exchanger essentially, and we use that to compute how the heat exchanger works. And for the bore field, we need the geometry. So actually, that's something we're still working on, so maybe I shouldn't go into too much detail to avoid making wrong statements. So in the second stage, we translate this model using the toolchain. It's a Modelica-based toolchain. Since the models we use are also Modelica. It's based on the open source framework JModelica, and we made some custom modifications to really generate a much more efficient code than what the default JModelica implementation does. So it's tailored to building applications, which we are working on, and essentially we were able to deal with a lot more states. In our case, our model has 1,200 state variables, whereas the gray box approach typically has in the order of 20 state variables. So it's different order of magnitudes that we're talking about there. Now, I'm not going to bore you with too much details, but I just want to give you a bit of an idea what makes this toolchain so special. So essentially, we have a model which contains a bunch of equations, which is this Modelica model. And what we do essentially is we split those equations out into 3 different parts. One part are these equations, so these continuous things that are only a function of time. Like weather forecasts, often they have a lot of computations underneath there, and these computations, they only depend on time, which means that they don't depend on optimization variables, which means you can pre-compute them. So these equations don't need to be part of the optimization problem. And that way we can just throw those out with the optimization code itself, and that makes it more efficient. And a second part is then the linear dynamics. So the building envelope itself is more or less linear. We linearize it. And since linear equations have certain mathematical properties, we can process those very efficiently. And then thirdly, we have these nonlinear equations, but they are not dynamic, so they are steady state. And those are essentially HVAC equations. And since these ones are simplified, we can evaluate those also very quickly. And then we have the executable. And now I just want to give you some simulation results from simulation study that we did on the MPC that we have developed so far. So what you see here at the top is outdoor temperature. So this goes sub-zero here, so it's a relatively cold period in Belgium that we're working on here. Solar radiation is plotted here, so there is still some sunlight also. And what we're essentially controlling is the two-way valves of the 4 floors. So these are depicted here, and you see a lot of variations. And it's a bit captured here in total by the heat flow rate that's flowing towards the taps. And you see this clear on-off behavior between day and night, where at night we need some additional heating to keep the temperature above the lower bound of 22 degrees here. So these are all the zone temperatures. And we have an upper bound for the zone temperature at 24. So that's pretty much automatically satisfied by the heat dissipation of the building. And this is different than what you typically see in a classical control of buildings, I think, where you use an average outdoor temperature to control the heat flow rate towards the building, and you will see a more steady profile. So the MPC is using its flexibility a lot more to heat more efficiently. This is the same period in the year where we focus a bit more on the ventilation part of the model predictive control. I didn't go into too much detail yet in this presentation, but I want to emphasize that we also control the ventilation, so the air handling unit. And in this case, what is important to note is that there is a CO2 concentration limit at 1,000 ppms. And you see here that we're going over this limit. And now, that's not a fault of the MPC, it's simply because in the simulation, the ventilation system is undersized. It's not a fault of the designer either, we just put the CO2 gains very high. But this is just to illustrate that in this case where we're reaching this limit that the VFVs automatically open completely. And you see also here that the supply pressure of the air handling unit goes up to the maximum of 180 pascals to be able to push down this value as much as possible. But this is just to illustrate that the MPC is working as you would expect. So trying to satisfy this constraint that it does whatever it can to reach it, and then when the constraint is satisfied, it becomes more energy efficient by lowering the supply pressure by closing VAV so that the overall fan power goes down significantly. This is a winter season. No, sorry, this is a cooling season, so it's a summer season where we have temperatures around 20 degrees. Solar radiation has gone up a lot, so if you compare essentially the area under these graphs, you see that we have a lot more solar gains here. So this is, just to be clear, this level of detail is included into the MPC. And you see here that we're in cooling mode since the TAP's thermal powers are now negative. And what is also important here is to note that the zone temperatures are now going up more. So we really need this cooling capabilities of the concrete core activation to stay below this 24 degrees C limit. And one thing I want to point out here is that, for instance, here you see that we have no total heat flow rate going towards the taps. So you may say that cooling and heating are both disabled, while in fact the individual heat flow rates of this taps are not zero. So some of them are cooling and some of them are heating, which essentially means that they're exchanging heat between them. So the system is now being used very efficiently to exchange heat between separate tap sections, which allows you to heat and cool at the same time by using just pump circulation power. And this is something that, with this level of detail, that the MPC can figure out by itself. And that makes it very interesting, of course, because you can save a lot of energy by doing this. What else can we see here? For instance, in this case, that you see very clearly that two valves are being closed and one is being opened fully. So there is clearly some cooling demand at this point, but just for one floor, and then only one floor is being actually cooled, which also drives down the total energy cost of the building. Another thing that we observed at some point, but I didn't illustrate it here, is that the actual heat pump was disabled, but heat was being drawn in from the air handling unit heating coil and being put into the concrete core activation. That's something we also saw at some point, that actually the air entering the building was being pre-cooled. That heat was then being dumped into the concrete core activation such that it could be cooled away at a later point. And these kind of things are very interesting if we start playing around with hydronic schematics that have a large degree of flexibility. Then I really expect that we're going to see some very interesting things pop up similar to that. Now, I haven't shown any energy savings yet because we haven't gone through the simulation procedure into sufficient detail to really, for me to say, okay, this is how much savings we get. But I did do a study on solar wind in my PhD, where I already mentioned 82% energy savings. So that's essentially this comparison here. And I just want to explain a bit more in that case how we got that energy savings. I also want to note at this point that it's not something we expect to get for every building, and we do deplete the thermal energy of the bore field. Well, the thermal balance of the bore field essentially is not maintained. So we inject 100 megawatt hours of energy and we withdraw only 6, while for the rule-based control this was more balanced. So it's not a sustainable solution, and that's something we still have to work on further. But still, this energy saving of 82% clearly shows a potential, and therefore we hope to get around 50 in practice. So where do we get these actual savings? First thing is that our COP goes up. So for the rule-based control, if you compute the COP from this, it was 4.5, and in the MPC we're getting a COP of 5.5. So that's just by controlling the system more appropriately, such that temperatures go down, that you can drive the COP up. The second thing is that we have a lot better coordination between ventilation and the concrete core activation. What sometimes happens is that you cool and ventilate at the same time using different systems, and MPC is very well able at doing that, and that drives this overall cooling and heating load down. For instance, here you see a reduction of the cooling load from the air handling units by a lot, but that of course shifts towards the bore field, which is then again a problem. But yeah, that's another part of the solution that we found. And the third part is the frequency control of pumps and fans. So classical controls typically put on the pump at full speed, while in our case we know that if we reduce the pump head by, let's say, 30%, we know how much mass flow rate we can still get, and that way we can do that, and that actually reduces the pump power by a lot. So here we saw that the pump power reduced from 15 megawatt hours to about 1 megawatt hour for the concrete core activation circulation pumps. And for the air handling units, we also got a strong reduction, which is partly realized by reducing the fan supply pressures at times where we don't need a lot of ventilation. So I've now come to the last part. So the demonstration is something we're actually working on right now. I can't tell that we activated it 2 days ago. Unfortunately, well, we activated it, let's say, a month ago, but we have had a lot of hiccups, and so at this point, something is running, but we're not writing control signals yet. So this is definitely work for the coming weeks. So just to give you a bit more details on that, for the actual demonstration, we we did an implementation of our algorithms on a virtual machine in Linux environment. And this machine can directly write on BACnet. It also has internet access for fetching weather data. And it does, so periodic download of every 15 minutes we get new weather forecasts. And the idea is that we every second read BACnet measurements and then do a closed, for instance, if we have some PID controls for doing the tracking of set points, we operate those at the lower, a faster update essentially than the weather forecast. So there are separate algorithms. We foresee to have a fallback on RPC, so on the rule-based control. If something goes wrong with the model predictive controller, we want it to jump off automatically to stop writing on BACnet, and then we can just fall back on the rule-based controller. That's something that we do now in this research stage, of course, to not send people home, but I hope at some point that we can just install MPC directly without having this fallback solution. And something that's also important in our case is how to do error handling. So if something goes wrong right now, we automatically send a message to a server which sends an SMS and an email to us, such that we know that something is going on. Now to give you an idea of what we're actually controlling, we have some figures. So this is an overview of the Priva interface, where we have these 4 two-way valves of the building. So those are valves that we are controlling. This is an overview of one of the floors, where you have the same two-way valve indicated here, but you also have some dampers for which we control the ventilation flow rate. So there's a damper for each of these 4 different rooms. And if there is a heating coil, for instance, as indicated here, then we can also control the flow rate going to that heating coil. This is this is the collector of the ventilation. The heating system. There are 3-way valves here that control the supply temperature towards the concrete core activation. There's a pump here that we can control. There are 2-way valves that choose between a heating system here, so heating system and a cooling system. So those we are also controlling. Then there is another circulation pump here at the heat exchanger for the bore field, which of course has to be enabled when needed. Here, this is an overview of the heat pumps and the circulation pumps. So we're controlling these 2 redundant circulation pumps. There are several valves here that allow you to shut down one of the 2 heat pumps. And so these are we're also controlling. And what else do we have here? It's a bypass valve here, a pump here. And I haven't shown everything yet, but it's just to show that to do such a control, there's quite some things that you need to consider, like redundant pumps, shut-off valves, etc. So these are all things that we have to take into account. Now to do the actual implementation, this is a bit of an overview of how it works in software and hardware. So the building essentially contains a lot of hardware, which is coupled to these HX controllers of Priva that actually do the analog control signals towards these components. And they are connected together over a BACnet interface. And currently we have this building management system which communicates with these controllers and gives them set points. And what we essentially want to do is hook up into this layer with our computer, so our virtual machine, and to also write on this layer. And to do the writing, we have essentially got a few scripts where I already mentioned that we have a script for getting weather forecasts. We have a script for checking whether our MPC is running, and if it's not running, to fall back on the existing rule-based controller, so to stop writing on this BACnet layer. And then we have a script that periodically repeats itself, for instance, once every hour, that actually computes set points for the various components in the system. And then we have another script that's operated at a faster sampling that tracks these set points. And we have some consistency checks, essentially, that first check whether these set points make sense, whether nothing went wrong. And then if everything is okay, then we can do the actual post-processing. Some implementation difficulties that we had so far are as follows. So we're installing something in an existing building which is not maintained by us, so we have to get the correct access rights. Also access rights for connecting to the internet even is not that obvious. And for writing on BACnet, we also had some difficulties with getting sufficient bandwidth. Well, maybe not bandwidth, but there is some delay on the writing, which is something actually we're still looking at. There were some malfunctioning motors that we figured out at some point that something was wrong, so we had to fix those. BACnet does not necessarily have unique variable names, so we had build something on top of the interface to make sure that we're addressing a unique device and things like that. So as a last slide, I think, to just give an overview again. So for this practical implementation, now we're in the implementation phase. We're not writing yet, but the algorithms are currently running, and we're getting emails all the time when something goes wrong, so it's very exciting. So we definitely know what to do, and the idea is to do a phased implementation where we start with controlling just a few variables to see how everything behaves, and then gradually control the entire building using all the variables that I discussed earlier. Then we have a second demonstration case called the Potterie, which is an elderly care home in Belgium of 10,000 square meters that we are currently preparing the model and doing preparations for implementing the controller on site. And then for SolarWind, we're still awaiting approval to do the actual control. So that's in a nutshell what we're working on right now. I think it's now the debate, so in case of questions, I think it's best to wait for that. Thank you.
Thank you, Philip. Now is the time for debate, which will be moderated by Wim Boydens from Boydens Engineering, one of the most significant and most probably the best engineering company in Belgium, Europe, world. Bruges, yes. I also have some info from our webinar. There's 20 more people, about 20 more people watching us online. So I think it's great to have also online people here. They will also, if you are watching us online, you have the possibility to write questions into the live chat that is somewhere on your computer window. And Carolina here will watch the chat and interpret the questions to Wim. The people that are here in the lecture room do not have to use the chat. They can just speak the questions out.
Yes, but please always raise your hand and I will bring you the microphone so people on the webinar can hear the question.
Yeah, so always use the microphone. So, Wim.
You only have one microphone?
We have two.
You have two. But
I hope this one is working, but it seems like it. So.
But then the people who are speaking should come forward so that I don't...
You raise their hand. Oh, yeah. Do you mean the presenters? Yes.
Yeah, otherwise I'm walking for miles. And is Eileen also a speaker, or you never know that there are questions for you? And then I'm missing Jan. Jan? Okay, so I guess the first thing is to see if the audience can break the silence and has some questions. And who's running up with a microphone? And please introduce yourself so we have an idea about who's talking.
Is this working? I don't think so. So hello, my name is Jiří Dostal. I'm from UCEEP, from the CPU University. Okay, closer to the mouth. My question to actually all of the white box approaches is, how do you, what's the validation score of your models? I mean, the white box approach is nice, but you still have to work from the design and datasheet data of all the valves, pumps, and so on. And of course, there is model mismatch. So what's your validation score of your model on the inflex, for example? Have you done so? Thank you.
Who urges to be the first?
So that's a very valid question, of course. As we know from the regular building simulation modeling, models are never perfect. And that's also what we see in the validation study that I did in my PhD, that you can be off by a lot even with this white box model. Now the thing is, how we cope with that is that we use the measurement data to correct that model essentially, to do a state update, and that's also the approach that's used by a gray box model. And I would argue that a gray box model is even less accurate, although it is calibrated, of course, using measurement data. Still, it has a bit the same problem. So just to show that if it works for gray box, it also works for white box. So that's more or less what we're relying on, is the state update.
That being said, for Infrax, as we are starting using this white box for MPC and we want to be as accurate as possible, we are also doing some validation by comparing measurement data with our model. So we measure what are the control actions and what's the actual temperature in the building. We also know the weather, and then we just simulate the building and we check whether there is a good match, and that's helped us to take some mistakes out of the model as well. What's also an additional point is that most of the models in IDS, we try to validate them on different cases where we have measurement data and where we have applied it to it. Of course, this might still be some, even though your physics might be correct, this might still be some modeling error or incorrect data sheets. And yeah, but we, on the long run, we, as Philip has said, we hope to get sufficiently accurate in our white box modeling, such that the state estimator is enough to correct the model for MPC, and that we do not need to do this very time-consuming validation, and that we can start with new buildings without having any measurement data.
And it would make sense, of course, to at some point go to a hybrid where we now say we have a white box model, but at some point it would make sense to also do the gray box approach on the white box model. So update the model based on measurements. Yeah, but that's research for the future.
No written questions yet? Okay.
Yeah, I have to present myself. My name is Lieve Helze. I'm from the University of Leuven, and I'm guiding these two guys in the MPC implementation. I have a question for Jan. Jan, you explained that the new MPC you have installed now has an RC model with 28 states?
Yes,
yeah?
it has.
Which you identified by both measurements and white box model results?
Yes, exactly. We tuned some parameters of the model, you know.
Did you check what extra accuracy you could gain by using the white box simulation results? I guess you first tried
not yet, because white box model has too many inputs, which has to be somehow estimated. I think the white box model, which was the linearized white box model, which was taken from Lydia's library, it has 150 states and 280 inputs, and you know, that's like and one input is, for example, I don't know. Yes, solar gains to each window, and so it's a long-term process for us to do it right now.
But my question is mainly about if you would identify your RC model, your controller model, which is not that very big white box model, in your case?
It was from RC model, primarily from RC model.
Yes.
Yes, but we had some simulation results from Modelica, so we refined the models somehow. Yeah.
as we are developing LIDS, I just want to clarify something. Indeed, the white box approach resulted into a controller model with many inputs, and in your case it's 200, in our case it's even more. But we have the models to actually generate these inputs based on a much fewer data. So we extract measurement data from an online website, and this is about 8 parameters that we need. So we need the global solar radiations, we need the dry bulb and the wet bulb temperature, and we need the wind speed, but not much more than that. So all the inputs that we need for our models are extractable from typical weather forecast sites, and we have then the model to generate all the necessary inputs.
Okay, so there are 3 questions on the chat. The first one is from Hem. My question is to Damien Picard. How accurate should the models be for the MPC to be better than functional rule-based PID controllers?
To start with, I would make a distinction between different type of buildings. If you have a typical American building, which is being heated up by mostly air-based system, and which does not have a lot of inertia, then the system is so fast that actually anticipating what you need to do is not that crucial. There, the PID might just strike in the heating case the lower bound for the comfort boundary, and their MPC will not have a strong added value compared to PI controller, even though you may have the perfect model. In the case of hybrid geotabs building, where we are using concrete core activation, there the inertia of the building is much bigger. For example, at home I have floor heating, and if I don't turn it on 6 hours before, I will be cold. So they start to be really important, and the PI controller cannot track this type of time constant. So there, even a quite simplistic MPC model will probably do better than a PI controller in that sense, because time constant is so crucial. Now, if you take a typical complex building with many zones and many different HVAC systems, the question is not so much what's the comparison between MPC and PI controller, but in general, what's the comparison between MPC and RBC? I can tell out of experience, we have colleagues who have started their own MPC company and who are modeling their whole building with one or just a couple of states. So extremely basic model. And they are not going to control with MPC each valve, but they are rather going to define, is it a heating mode or a cooling mode? And do we anticipate that we need a lot of cooling? And so would it be useful to pre-cool the building? So in this sense, the building model is extremely simple, so inaccurate, and still they have savings of about 10 to 25% of energy savings. And I would like to conclude that in this project, especially at the K11, where we really focus on the white box, we want to optimize up to component level. There it starts to be much more important to have accurate MPC models, because if we actually start controlling a valve with MPC, that's a really low control. If there we make a strong mistake in estimation, then we are going to perform less well than the typical RBC. But please keep following the result of the project, and you will get your answer, hopefully demonstrated in different buildings.
If I can add to that, the point of MPC is not just energy savings, because we're focusing a bit on that, because it's of course in terms of our environmental impact quite important. But we hope also at some point that it becomes easier and more robust, and you need less commissioning to do MPC. So that also there you can gain a lot. Yeah, so that's something I wanted to add.
Okay, thank you. Then we have already 3 questions from Danny Austin. Okay, first one, there are 2 for Philip. The first one is, one mentions a potential gain of 82%, 50% in practice, in energy saving by MPC. What are the main drivers? What are their actual contribution in percent of total?
Yeah, so I think I covered that during the slides, but I'll just go over that again quickly. So part of it is the COP that increases from 4.5 to 5.5, which is then just on the heating loads, an efficiency increase of 20%. So in the overall energy budget, it's not that much. Where we also gained a lot was on the frequency control of pumps and fans, which had a much larger impact. I think that's where we got savings in the order of 70% on that part of the load, which was in the order of, let's say, 30%. And then the remaining gains were mostly on coordinating heating and cooling loads of the building, where it happened that we were in heating mode because simply that's what what the rule-based controller determined based on the average outdoor temperature. And due to being in heating mode, there was injection of heat into the building while it didn't actually need heating, so the ventilation system had to cool it off again, and that drove the energy cost up quite a bit, and we were able to avoid that, which I think it has the largest impact of the overall result.
Okay, thank you. The second one is, you started with the implementation on Infrax building. What are the main hurdles you have encountered so far?
Yeah, so to summarize that one also, we had a lot of hurdles, but it's perhaps best to summarize it as actually doing the implementation in terms of communication and learning to work also with BACnet. So, for instance, we had to get access to the system through a virtual VPN service, which we had some issues logging in. We had to learn how this login works, the robustness issues. We had to use a proxy to connect to outdoor servers and all these kind of things. So it's mostly these practical things that we had to learn essentially how to work with everything. Now, actually, Damien has a bit more experience with that than I have, so perhaps you have something to add.
Our experience as well is that BACnet is an international protocol which is many manufacturers provide, so the possibility to communicate with different machines through it. In practice, it's a bit different. Often, even though there is the functionality to have it, it might not be activated, for example, or there might be only a subset of variables which are accessible on it. So there we spent a considerable of time for the Infrax building. It's an old technology, 10 years ago, and that did not support BACnet, so we had to add additional hardware there, BACnet router basically, to have access to it, and then we had troubles even though all the BACnet variables were available on the network, we could not read the present value, for example, so we had to solve this. Other problem is that sometimes the Infrax building, we saw these two-way valves for the concrete core activation. These are actually spherical valves there, which are not really meant to control flow, but later they decided they wanted to control flow, and then they added a motor attached to this valve. These are extremely simple technology that they use. It's a 3-point control, and it turned out that actually the motor did not work properly and could not be the actual angle of the valve could not be accurately controlled. And these are things that when you commission your building in RBC, these are things which are difficult to detect because you often don't have a flow sensor, for example, in your tap circuit, so you don't really know whether it's working properly or not. And then also, after 10 years, it has been at least 8 years that there is no commissioning on it. So then you discover actually many flows which have occurred during the last years and that we have to solve as well. We hope that we will encounter less problems with a more like a newer building. I'm not speaking about solar wind and the elderly care home. So that's the thing, is that I think to summarize, the major issue is that often buildings are not properly commissioned because it's so time consuming. And when we actually look into details, into controlling everything, then we discover the problems. And that's also something we hope to have more into control with MPC, as we have models and we know what to expect from the building. And if we see that it's not happening what we expect, then there's either a model problem or also likely there is a hardware or a software problem.
Okay, thank you. And then there's the last one from the chat. Where do you expect to be the largest deficiencies in correct representations of the physics in today models employed as cause of the errors in heat demand prediction?
Can you repeat the question, please?
Okay. Where do you expect to be the largest deficiencies in correct representation of the physics in today models employed as cause for the errors in heat demand prediction?
Maybe I will start and then I will give over to you.
It's a general question.
So,
okay, I will bring it to you then.
Just to rephrase it, we know that physical models are not always always really accurate, and where is the biggest source of inaccuracy in our model. I think that's how I understood it. So in our experience, something which has an increasingly importance is the. Sorry, I will start again. Buildings are more and more insulated, and often the surface of glazing is quite important. So solar gains start to be really important, not so much for heating, but mostly for cooling. So correctly guessing or predicting what will be the influence of solar gains is very important. And there's not so much the physical equations which is inaccurate, but rather the forecast. Having decent solar radiation forecast is very tricky. So my guess is that as buildings need more and more cooling, that is a major challenge to get this right. A second aspect that is tricky is the difference between the design of the building and the as-built building. That's something we hope will be solved more and more with the BIM approach, where they try to centralize all the information into one database, which is then available for everybody during design and after design. Because our concern is that the document we get about the building are often outdated and do not correspond with the actual layout of the building. And I think there will be a major source also of problems. So not so much about the physical equations, but a lot about information that we get. And maybe Philip could say something also about inaccuracy of model, about stratified temperature, for example, in big.
You read my mind. So one thing I was indeed thinking is the bit limitations of the zone temperature model, so air temperature model that we currently have. So it's a perfectly mixed model with fixed correlations for heat transfer between the walls and the zone node. So we linearize those equations, and essentially you have some heat transfer effectivity, and that's probably not that correct, and that's the way it is. And it would be great to have a more detailed model, but unfortunately, computationally, that's not that obvious. So that's one thing I think about, that's certainly a limitation, but on the other hand, that's what we have this feedback for. So it shouldn't be an issue because we can use measurements and correct for that. And I agree with what Amien said. Is second part then is that forecasting your heat gains essentially into the building, partly from windows, but also from occupants and devices. It's not that easy, and something I hope also to be able to correct based on measurements from the building. You want to add something?
Okay. Then I will still add something about the gray box approach. There, it's also very important to understand that when you have a multi-zone building, it's extremely difficult to capture from measurement data the interaction between the different zones, where they are actually pretty important. So if you think about our white box approach, which is a complex model of more than 100 states with thousands of parameters and a lot of different inputs, if you try to fit just based on measurement data that amount of complexity, you will fail, because your temperature in your building is also relatively constant, so it's not that informative. It's very difficult to know. A wall is actually a massive element, and to know how massive it is, you would need to cool it down for many hours to see how long it takes to actually cool it down to the core, and then only you will know how much heat capacity was in that wall. That's something you cannot extract from measurement, except if you excite your building tremendously and during a long time. I'm not saying that MPC does needs that level of details. Maybe it's enough to know just that there is a wall and roughly estimate how thick it is. So gray box models will face a very challenge to get like really accurate models. And the more relevant question is whether it's necessary for MPC or not. I think there is a whole debate in the community, and the American approach is that that's definitely not necessary to have detailed building approach, but it's just because they're building your air-based and light structure, very fast reacting, which is not the case. If we look at this building, how massive it is, there you will have a lot of trouble, I think, with gray box approach to really know what's the inertia of your building.
Thank you, Damien. I hope this clarifies a little the question. We have someone from the audience, 2 persons from the audience.
Okay, so I'm Jelle Lavage from Ghent University, and I had a question for both Damien and Philippe because they showed similar slides. So well, the slides I want to ask a question about were similar. So you both had a slide where you showed a hydraulic scheme which had basically duplicate units. 2 times the same pump, 2 times the same heat pump, 6 times the same heat pump. How does your MPC solution approach controlling things that are basically the same and that are hydraulically in parallel, and are there advantages or disadvantages to the way that this is then controlled by the MPC?
So let's take the case of a heat pump. For instance, in SolarWind, there were 4 heat pumps which had 2 distinct sizes. And if you do the math, that means that you can have 8 stages because they are on-off controlled heat pumps. So since our toolchain right now does not support the use of binary variables, so on-off, we took an approach to merge those 4 heat pumps into one and to pretend that we can control that continuously. So that's a bit due to the limitations of the toolchain that we took that approach, but at some point what would be ideal is that you can just consider those 4 individually and each of them have separate set points, and then just have the optimization directly optimize it and see whatever comes out. I think in a performance perspective, the difference will not be that much, but it's mostly in terms of usability, since we really want to go to this one-to-one mapping, that you don't have to think about what you're doing, you just push it into the model and it should work. I think that is the biggest advantages. So that's my first take on that. And in case of the parallel pumps, it's not really a performance matter, it's like a redundancy matter, if I understand correctly. So I think that's also how we should treat it, and then perhaps consider only one pump and do some sort of post-processing that we automatically switch between the 2 and then switch to the other one if one is broken. So to grasp that complexity also into the MPC.
Yeah, so on the parallel pump, I think the redundant pump for the bore field in the MPC will consider it as a single pump, and the post-processing will switch from one to the other to make sure that the number of working hours of both pumps is the same. But where I want to add a comment is for the heat pumps, and also for cooling machine, because that's really the hot topic, if I may say, of MPC in America. It's that you have a big difference of efficiency if you work at the part load ratio that if you work on foot load ratio. So if you have 2 identical cooling machine in parallel, MPC will really clearly know what's the optimal solution, namely you use them both in part load ratio instead of using one full load and the other one not. So that's also interesting, is that you also know how to use your different machines and how to use their strengths combined. So we should always be careful that there is indeed hopefully a unique solution to our optimization problem. And if there is true redundancy, that might not be the case. So that's something we have to keep an eye on. But I think that in most of cases, there is one unique optimal solution.
name is Jan Cherokee. I'm from the company Energocentrum, and we are collaborating on some MPC projects with Czech guys as well. And I got a question probably to Philippe regarding the MPC scheme. You showed something that could be seen as a hierarchical control, where you have a MPC with 1 hour period, and this is the picture. And below there are some let's say low-level controllers with 15 and 1 minute period. And my question is, how you decide what should be controlled by MPC and what should be done by low-level controller? Because at one side you would like to take into account all the parameters in the optimization, but on the other you cannot end up. You can end up with some infeasible model or with something that will be not feasible in real-time operation. So if you have some general guidelines, because each building is individual, and probably one of the outcomes should be some guidelines or some proposals how to decide this distinction between higher and lower level.
That's something we partly still have to figure out based on experience, of course, but the approach that we use right now is to put as much as possible into the MPC and to switch to post-processing if we expect that the MPC model is not accurate enough. So to give an concrete example is we directly control the valve two-way openings of the concrete core activation, but we don't expect that we can very correctly predict the flow rate that goes through the concrete core activation, simply because the valve characteristic is not known that well. And so what we do is not apply this valve position directly, but track the outlet temperature of the return temperature of the concrete core activation that is computed by the MPC. So, and that's more or less in general how we hope to approach it for now, and then at some point we should be able to learn also from the measurements that we observe in the errors in the measurements that we observe to correct our model, such that even this post-processing hopefully isn't necessary anymore. But at this stage I think we need it, and that's a bit the approach. And you mentioned I think some computational issue. Right now the optimizations run in about 30 seconds, let's say, even faster. So could even go to real-time operation directly using MPC if we include the correct dynamics into the model. But that's something, for now I think we should leave it as it is. But there is still room for improvement in speed on the one hand, but also to exploit the fact that we're 100 times faster than real-time, essentially.
And maybe a really practical guideline, look at indeed how much does it take for your optimization to run, and then you know that you cannot control anything beyond that, like which goes faster than that. So I think you always will end up with some PI controller at one point if you want to control on second base. Doesn't make sense to run the whole optimization which predicts 3 days of operation of the building and to actually control as well like time step of seconds into your MPC, because that's going to also explode the optimization time. So right now we are applying steps of an hour, I think, in MPC for infrax. When we will include the ventilations and so on, we hope to, to go down to 15 minutes, but not on second base. And there will still be some post-processing necessary. So the guideline is not so much about what's the convergence of your MPC, it's rather what's the time scales in your building and how far does it make sense to optimize, but really thinking about time scales actually.
Thank you, Damien. I think the last question from the audience, if that's okay with everybody. Maybe one but last.
My name is Martin Kotzek from Vienna University of Technology. First of all, I want to thank you for these very instructive and nice presentations. I want to add, first of all, a comment on the problem of having redundant and combined switched and continuous control variables, because in our experience it really makes a difference to consider this actually mixed integer optimization problem. Because if you do post-processing, then mostly it's done not in a predictive way, and especially if you have cooling machines or heat pump, then you have a unit commitment problem, and time and the prediction over time is really important. So this, I have a question concerning the white box model, especially the structuring in zones, in building zones. So what were the criteria for selecting specific zones? Also, is there the coupling between the zones considered? And last of all, if you do one large building model with several hundred states and you do one optimization for the MPC, how do the zones come into play?
And not specific for one of the buildings, just in general.
Okay, so I'm gonna lose you halfway, but let's start with the zone coupling. So we do consider the zones to be coupled. For instance, in a concrete core activation, this can be quite important. If you have a floor slab in between two zones, and you clearly have an effect on both, that's something we want to capture. And also just because it's easier to do it, because it would be a hurdle for us to separate everything out rather than just putting it in as it is right now, because that's the way ideas has been built up. So then now I lost you with the rest of the questions. Can you? Yeah, okay, so with we essentially base ourselves on the HVAC right now, because essentially zoning has been implicitly defined using the HVAC. So for instance, in SolarWind, we have 6 circuits per floor, which we then use to, the same floor plan is used as one zone right now. And you could go into finer detail. For instance, if you have a subdivision within that zone for the VAVs, which is actually now the case in Infrax, because we have one a concrete core activation system per floor, and then we make a subdivision based on VAVs. So in that sense, I think it's still pretty straightforward to do a mapping, but it takes some thinking, of course. But at some point, we would like to make that even an abstraction there that you don't need to do a zoning anymore yourself. You just give the geometry and the model figures out what it needs. But that's further development essentially.
Additionally, for topoterie, we have, for example, many rooms. That's an elderly care home, so there are many rooms, bedrooms for the people living there, and there are many. So there might be one radiator in each room. So you may say, I want to control each radiator, but if they're all similar rooms facing a similar orientation, it's logical to lump them. So the first thing we see, what can we control? And if we have too many control variables, so each radiators, and that we can lump, and which can truly benefit from having the same control, that's also how we are going to lump. And then I would like to answer your question about mixed integer programming. That's the approach which is being done by Johnson Control for the Stanford University campus that I've shown, hierarchical MPC and mixed integer programming. And we clearly see the benefit of mixed integer programming. The problem, and then Philip can say more about it, is that it's not implemented yet into Gemodelica software that Philip has been adapting for MPC. So that would require a lot of work to actually implement it. There is an added value, but it's not quantified either how important it is. And we are right now handling it. For example, if we have a continuous, so if we have something which should normally be controlled on a discrete way, we would control it on a continuous way, and then in the post-processing, either use pulse-wise modulations to get it correct, or just to decide based on a threshold whether it should be on or off, which is suboptimal. I completely agree. And we really encounter that problem with circulation pump, which are not frequency-based. And sometimes we are obliged to keep them on just to be able to control it, while actually if the optimization could control it correctly, then it would switch them off more often.
Yeah, so I agree there also that mixed integer would be a lot more clean solution. It would also drive up computation time by a lot probably, so that's a bit of a hurdle there. One issue is indeed that JModelica does not currently support integer decision variables, neither does IPOpt. There exists open source solvers that do support it, and there are plans to extend JModelica, so it's something we definitely want to look into. But before we're there, it could be an option to either to do a bit more advanced relaxation, where you use complementarity constraints to try to mimic the integer behavior. Another solution is to do a two-stage optimization where you do first a relaxed optimization, and then if you get a modulation of 0.2, for instance, you fix that to 0, and then you do a second stage optimization, and then you do take into account the actual capacity of the heat pump and work with that. And okay, it's not optimal, but I think there's a lot more to gain by just having MPC rather than having the actual optimum of the control solution. One final thing I would like to add is that typically the systems that we control, well, firstly, maybe the system that we're controlling, so the building, is a continuous system. You have got disturbances that are completely continuous, people going in and out, heat flow rates. So it makes sense to be able to control it as a continuous system also. So for me, actually, I would turn it around and guys, stop using on-off pumps, stop using on-off heat pumps. It's a bad idea, stop doing it, seriously. And so in the longer run, I think we won't have this issue anymore. And we can gain a lot from using these frequency controlled also.
Thank you, Philippe. So the HVAC industry in Europe has a new challenge with your declaration. And we have one too. Whose priority coffee are you? Okay, last question, and then we go for coffee. Time consumption of the modeling. Okay. Okay, think about the time.
Yeah. So I think we should get to a point where MPC implementation is faster than rule-based control, so where we can do it in a few days for a big building. And essentially, not to go into too much detail, but I showed now the Modelica interface, which is not very user-friendly. We want to build a layer on top of that where you have a more normal interface like what you expect in typical building energy simulation programs, which is really drag and drop, plug and play. And in the longer run, we could do a BIM to Modelica conversion automatically if you have BIM schematics, and then it's just, automatically.
Just a few days might not be the right scale. Like if we combine all the effort being done by engineering office to describe the control, plus the actual programming of the installer to get it down in the platform of Honeywell or Priva and so on, and get the commissioning, it's way longer than a couple of days. So I think we should not be that strict with ourselves with MPC. We have time.
Thank you very much. So for those far and abroad, at around 12, we are restarting. And where's the coffee? Up there?